Hello everybody, my name is Morris Wan and welcome to my lab report for Physics Lab 2. So in this lab, we are looking at the motion of a falling object and utilizing Newton's second law of motion to help predict that motion. So we initially used a model using just constant force, being gravity, and then we also ended up using a model that incorporated drag into the equation. And ultimately, we were able to create an acceptable model that used the momentum principle and the Newton's second law of motion, as well as both drag and gravity, to accurately model the motion of an object. So the particular object that we used in this lab was a balled up piece of paper. And so as you can see, we drop it from a height of my fully extended arm down to the ground. So here's the tracker video of that motion. A possible source of error here, as you can see, is that the ball did not fall completely straight. It fell slightly to the left in the x direction. Again, and also the point masses weren't quite right. And so how we ultimately tracked it in Tracker is that we set the origin of the coordinate plane to the center of the ball as right before it was dropped, and then we put point masses in the center of the ball as it dropped down to the ground. And we use a coordination stick of my height, 1.727 meters, as a point of reference to determine how far it was falling. And again, the camera quality and the human error led to relatively inaccurate or sometimes inaccurate point mass locations. So as you can see, the line isn't completely straight. There's some wiggles in there. But ultimately, it was a pretty solid approximation of the observed motion of the ball. So here's the model without drag, and here's the model with drag. And so as you can see, when we plot all three of these on the same plot, we can see that the model with drag actually approximates the motion of the ball a lot better than the model without drag. Both of them are relatively good approximations up until near the end of the motion of the ball, where the model with drag is much closer than the model without drag. Again, it still under approximates the observed or compared to the observed motion. However, it's still a relatively good model of the observed motion. And so a question that was proposed was, does this ball during this time period approximately reach a point known as terminal velocity, where the change in velocity of the object becomes zero? So during the time that it fell, it actually did not reach this kind of terminal velocity concept. The velocity was still changing up until the point that it hit the ground. However, if we use the same model, being the drag model that incorporated both drag and gravity, and extrapolate, we're actually able to find that it does eventually reach a terminal velocity point, and the velocity stops changing. And this point ended up being at about negative 5.3 meters per second in the y direction. And so another question that was brought up was, what happens if the ball was thrown down with an initial velocity of 2 meters per second? So as we can see here, the ball during the time period, similar to the previous example, during the time period, the velocity is still changing. However, if we extrapolate again at around the same time, possibly just a little bit later, the ball reaches a terminal velocity, essentially, where the velocity doesn't change, and it reaches the exact same terminal velocity at about 5.3 meters per second. So it doesn't appear to matter that even though it has an initial velocity, it will still ultimately reach the same initial velocity, perhaps just a little bit slower. So here's the code that I used to model the motion of the object in GlowScript. So as you can see, we use arrows to model the drag and the gravity force. And if we look at the code, here we have the mass of the ball. So the ball was approximated to be about the mass of a sheet of paper, which is about 0.005 kilograms. These are the ball's initial position and velocity vector. The delta t was measured based on the frame rate of the camera, so it ended up being about 0.033 seconds per frame. This is the acceleration due to gravity on Earth's surface. This was the constant of proportionality that for the drag force, which was proportional to the velocity squared. Again, this could have been potentially even more optimized if we went to further decimal points. However, this appeared to be the best one after two significant figures, if you will. And so here in the code is where I calculate the drag force and the force of gravity, and here's where I find the net force acting on the system, and here is where I'm ultimately using Newton's second law and the momentum principle to update velocity and then ultimately update position. That is about it. Thank you for watching.